For the sake of creativity, I need to set a few ground rules. First, we can't use the Miles Morales method, MMM, to achieve perfect accuracy, then use that knowledge to deliberately output wrong answers. Second, we can't train machine learning models like normal, except just switch what they're optimized for, like maximizing error instead of minimizing error. Third, like and subscribe. The boring approach is to just draw a random line infinitely far away from the points of our dataset. So we won't do that. To recap, linear regression basically involves drawing a line of best fit for a set of points. So instead, let's draw a line of worst fit. Step 1. Use gradient descent or similar to determine the slope of the line that best fits the data. Step 2. Take the negative reciprocal of that slope, which will allow us to draw a line perpendicular to the line of best fit, with a randomly generated y-intercept, I guess. In k-nearest neighbors, you take either the mean or the mode of class labels from the k-nearest data points as the predicted class label for an input data point. But I know what you're thinking, and no, we won't just do k furthest neighbors. Instead, I was thinking of doing n nearest neighbors, abbreviated as NNN, triple N. As the name suggests, we take either the mean or the mode of class labels from the n nearest data points, out of n total data points. I mean, the more data we use for each prediction, the better, no? We're only going to tweak decision trees a little bit to make some decision graphs. First, let's convert every feature into a categorical one, and not by binning numerical features either like some kind of loser. Instead, each numerical value will correspond to a distinct categorical value. Next, let's assign each feature to a unique node, then create a randomly directed outedge for each categorical feature value corresponding to each feature. We'll then predict the value of an input with the following procedure. Step 1. Pick random node. Step 2. Pick a random outedge and move to its corresponding node. Step 3. Repeat step 2 a total of, let's say, 10 to the 9 plus 7 times. Step 4. Pick a random outedge of the current node and output the most common class label of all the data points corresponding to that outedge. Step 5. Calculate the Gini purity or whatever. The term support vector machine is kind of a misnomer, no? I mean, it separates groups of points by drawing hyperplanes that maximize the distance between boundaries and their nearest data points. Where's the support? That's not right, so we're going to create supportive vector machines. This time, we'll make that aforementioned distance as small as possible, like this. And when a boundary slices through a point, like this, we'll say it's a mix of multiple groups. Like, if we're classifying species, we can have a half dog, half cat, or half dog, half human, for example. Naive Bayes treats all features as completely independent, which is rarely true in the real world, earning it the moniker of naive. So, let's make Wise Bayes, where we'll treat all features as completely dependent. Basically, if a perfect match to an input case appears anywhere within the training set, we output the average class value of all those training points. Of course, if no training data point matches our input for every single feature exactly, we'll just raise an error and divide by 0 or something and call it a day. You know what? I'm tired of making purposely bad machine learning algorithms, so I'm actually going to create a really good variation of a neural network with an idea I've actually had for a while now. Basically, I only want to change one part, the activation function. Instead of using the garbage activation functions everybody else uses, why don't we just use an elegant and clean activation function, like f of x equals x. Don't worry guys, I'll dedicate my Nobel Prize acceptance speech to my most loyal subscribers.